Okay, let us continue. So even if you missed some of the derivations, okay, so I'm going to summarize just the equations here, because now what matters is like how we are going to learn these parameters. So we are looking at Gaussian discriminant analysis. Okay, where the probability of C1 given X is given by sigma of W transpose X plus W0. Okay, where W is sigma inverse of mu1 minus mu2, and W0 is minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln P of C1 divided by P of C2. Is that clear? So the previous part was deriving how this classifier was designed. But now let's say this is given to us. Okay. Now there are a couple of observations here. So first of all, this ended up being a generalized linear model instead of a nonlinear model because of this assumption that the covariance matrices are shared, right? Had you not shared the covariance matrices, then you're going to have the x square terms in this equation. So that makes the model nonlinear. This is a generalized linear model because it's sigma of some linear model, yeah?
When you talk about the shared covariance, is the covariance for class 1 and covariance for class 2 with respect to the output?
So probability of X given C1 and probability of X given C2. So the covariance matrices of the class conditional densities. Okay. Now, so that is the first observation. The second assumption, the second observation here is you can see that the prior probabilities P of CK, they entered this model only through the bias, right? So you don't have P of CK in W term. You have the P of CK only in the W0 term, which is the bias of the model, right? Now we know that the bias is there to just change the boundary. So if you have a prior probability distribution about the classes, then this prior probability is used to change your boundary, but then other aspects of the boundary are learned by the W thing. Is that clear? Like, which is basically the mean and averages, like mean and covariance matrices of class conditional density. Okay, so now let us look at an example, right? So here is an example where I have the class conditional densities for two classes here. Okay, so you see probability of, I don't know what are the blue and red classes, but okay, so based on the right side, this should be C1. So this is P of C1 given X. Okay, and the blue is P of C2 given X. Sorry, these are densities, right? So this is P of X given C1, and this is P of X given C2. Okay, now you use Bayes' rule and compute the update equation for GDA. So then you get this P of C1 given X. Okay, now you can see that in this specific region, right? In this specific region, it is more of class 1, right? And in this specific region, it is more of class 0. Sorry, class 2. You can call it class 2 or class 0. It doesn't matter. Let's just to be consistent, let us call this as class 0. Okay. So you can see that the probability of C1 given X is very high in the left side, and it is very low in the right side, which is kind of capturing this P of X given C1 and P of X given C2, but with the Bayes rule. Is that clear? Okay. Now, of course, the most interesting aspect here is like, so how do I learn these parameters of this model first of all, right? Like, so once I have the parameters learned, then everything else is already well discussed. Okay, so how to learn the parameters. Okay. So in the case of linear regression, we discussed like a closed form solution, and we also discussed gradient descent for learning the parameters, right? Now, first here we are going to start with, well, this is a simple model, so we are going to start with closed form solutions, okay? And once we progress to more complex probabilistic models, we are going to start using gradient descent, okay? So for now, we can compute the gradients by hand, so we are going to do it. Okay, now, even before that, what do we need to learn the parameters, first of all? So we have the data, we have the model, so what else do we need? How do you learn the parameters of a model from data? Yeah?
The initial values, you just take random. No.
Well, you need the initial values if you're doing gradient descent, okay, so, but we are not going to do gradient descent now, yeah? Statistics, what do you mean by statistics?
Do you know the mean value, for example?
Oh, that is what we are going to estimate, okay? So how do you, like, what do we need to, okay, let's take linear regression, right? So we had W transpose X plus W0, and I gave you a data set. So how did you compute W transpose and W0? By using the data set? Yeah?
We minimize the error function.
We minimize the error function, right? Like in some sense, we need an error function that we are going to minimize to find the parameters, right? So now one could minimize an error function or maximize some other like positive function. Okay? So now for today, we are going to talk about a new objective function, okay? But the goal is to maximize this objective function by finding the parameters which maximizes it, okay? Now, how to do that? Let us start with some data set, okay? I'm going to call this data set as D, okay? So which is basically a bunch of examples, xn and tn. N is equal to 1 to capital, okay? So I have n examples, and all these n examples have pairs, xn and tn, okay? Now this tn is going to be 1 for class 1, and tn is going to be 0 for class C2, if you have two classes. Is that clear? Okay. Now, first we need prior probabilities, right? So let us call probability of C1, the prior probability for class 1 to be pi, okay? So this is basically the prior probability for C1. And can someone tell me what is P of C2 then? 1 minus pi, right? Because there are only two classes. So this is 1 minus pi. Okay. Now, consider some random data point. Okay. So you consider data point x. Okay. Now, first, let us try to compute the probability of xn. Okay. Comma C1. Like this is some data point xn. Okay. Now, what would be the joint probability of this data point, comma, class 1? Okay. So this is basically P of C1 multiplied by P of xn given C1. Is that right? It is just chain rule, right? So P of x, comma, C is P of C multiplied by P of x given C. Okay. Now, P of C1 is given by pi multiplied by the probability of xn given C1 is the class conditional density for class 1, right? So it's a Gaussian. So it's basically a Gaussian, okay, centered at xn given mu1 and sigma. Is that clear? Now, similarly, I can write what is the probability of xn, comma, C2. It is nothing but 1 minus pi multiplied by a Gaussian, but with mean mu2 and same sigma. Okay. Now, I can compute. So what I'm introducing here newly is the likelihood of the data point xn comma tn, okay, as follows. Okay, so what do I mean by likelihood? So given a probability distribution for this data, how likely is that I see this xn tn? Okay, now this likelihood capture is just captured by the probability, right? Like, so when I ask you how likely is this xn tn to occur, then you will just compute what is p of xn tn, right? So now this probability of xn tn has two options. Either it could come from class 1 or it could come from class 2, right? So if it comes from class 1, then the likelihood is given by pi multiplied by the Gaussian for class 1. Is that right? If it comes from class 2, so then it is given by 1 minus pi Gaussian of xn given mu 2 sigma, right? Now, instead of having these two if conditions, I can put them together in a compact equation. Okay, so all I have to do is have a power of t of n here and have a power of 1 minus t of n here. Okay, so now this equation actually kind of compresses both the probabilities. Okay, so if this data point actually comes from class 1, then we know that t of n is equal to 1, right? And this is going to be 1 minus 1, 0. So this whole term will go away. The probability is just pi multiplied by class 1 Gaussian, right? Similarly, if this data point is actually coming from class 2, then we know that t of n is equal to 0. So this whole thing goes away, okay? And you only have this thing. So 1 minus 0 is 1. So the probability is given by this, right? So this is just a compact notation for the probability of x comma some class. So the class could be 1 or 2. Depending on that, you will have one of these two terms. Is that clear? Okay, so we are going to, okay, this is very important. So we are going to call this as the likelihood of the data point. Okay, so before I tell you, okay, first of all, this is the likelihood of one data point, right? Now, one way to set up an objective function for finding the parameters is to say, I want to find the parameters theta. Okay, in this case, the theta is mean, covariance, p of c1, p of c2. Okay, such that, or maybe I want to find some parameters theta that maximizes the likelihood of the data set D. Okay, you give me a data set. Okay, the goal here is to find the parameters that maximizes the likelihood of seeing the data, or in other words, fit a probabilistic model which gives maximum probability to the data set in hand. So the hope is if you can find such a model, then it is going to assign like good probability for even examples that you have not seen so far, right? Like if it is capturing the distribution, then it is going to act like a better classifier. Is that clear? Now, to construct the likelihood of the entire data set, right? Like we are going to make a crucial assumption here. Okay, so we're going to assume that the examples in the data set are independent and identically distributed. Okay, or in other words, we will also call this as an IID assumption. Okay, so the IID assumption means that if I have 100 examples in my data set, they are all independent. Or in other words, the probability of the entire data set is given by the product of the probability of individual data points because they are all independent. Okay, and they are all identically distributed, which means they all come from the same distribution. that clear? So if I have the IID assumption, then the probability of the data given some pi mu1, mu2, sigma, okay, is given by product over n is equal to 1 to capital N, okay, the likelihood of each data point separately. So pi times the Gaussian for the first class conditional density, the whole power T of N, 1 minus pi times the Gaussian for the second class conditional density, power 1 minus T of N, the whole thing. Is that clear? Now this is the likelihood of the entire data set. Now this is based on two crucial assumptions here. Like the first assumption is all the examples are independently distributed. So that is how I was able to just do a product over all the examples, okay? And they are also identically distributed, which means they all come from the same Gaussian. Is that clear? Now, as you will see throughout this course, this IID assumption is one of the most common assumptions that all the machine learning algorithms are going to use, okay? So now, what happens when this assumption is violated in the real life, right? Like, so what happens when there is dependency between the scenarios and examples, right? Like, so now, probably the non-IID setting is out of scope for this course, but you can extend some of these algorithms to non-IID settings, okay? So, but we're not going to talk about non-IID settings in this course. So for most of this course, like we will just assume that all our data comes from IID assumption, so they are independent and identically distributed. Is that clear? Okay. Now this is the likelihood function. Okay. Now the goal of GDA is to find parameters that maximizes the likelihood function. Is that clear? Now, if you want to maximize this value, right? First of all, it's a product of n values. So if you have 100 data points, it's a product of 100 values. If you have 1,000 data points, it's a product of 1,000 values, okay? So, and these individual things are probability distributions by themselves. So when you multiply thousands of values which are less than 1, you're going to have numerical instabilities and underflow, overflow issues, right? So often, both practically and also theoretically, like it is just difficult to deal with the product, okay? So to avoid that, we are going to make one simple change, okay? So instead of maximizing this likelihood, we are going to compute a log of this and maximize the log likelihood, okay? Because log just captures the same thing, right? So maximum that you find in log is also same as the one that you find in the original space. So instead of considering this, I'm going to consider ln p of d given pi mu1 mu2 sigma. Okay. So when I do ln, like product becomes sum, right? So this becomes summation over n is equal to 1 to capital N ln of, okay. Now when you do ln of this, the exponent comes to the front. So it becomes T of n times ln pi Gaussian mu1, okay. Plus, the product becomes plus 1 minus T of n times ln pi, sorry, ln 1 minus pi Gaussian given mu2 sigma. Is that clear? Any questions? Okay, I think I skipped a step from the book, from the notes, but it is very clear. Yeah.
Just add one too many logarithms.
Oh, okay. So Okay, so there should not be ln here. Is that correct? I was about to write the first step, but then I skipped it. So, okay, is this correct? Okay, so now we have an objective function, but there's a small change here. Like, so in the case of linear regression, we had an error function, so we wanted to minimize the error function. But in this case, we have like a good objective function. It is not error, so I can just maximize this. Okay. Now, in general, like when we do gradient descent, we always want to minimize things. Okay. You can easily construct this to a minimize. You can transform this to a minimization problem. How? So our goal is to maximize this, right? Like, so our goal is to maximize ln p of d given pi mu1 mu2 sigma. So the goal is to find pi mu1 mu2 and sigma, which maximizes this. Okay. So how do I convert this to a minimization problem? Anyone? Maybe from the back or the right corner? Okay, yeah, you.
So you can just put a minus?
Yeah, you can just put a minus, and then like it is a, like when you do minimize. Okay, so when you do minimum of minus ln p of d given pi mu1 mu2 sigma, so this is same as the other one, right? So the values that you're going to find is going to be same. So this term is known as log likelihood. Okay, but often in different textbooks, you will also see people minimizing the second term instead of maximizing the first term. Okay, so the second term, right, like the minus of ln. So this is known as negative log likelihood. Okay, so in general, you can do one of these two things. Okay, you can either maximize the log likelihood or minimize the negative log likelihood, NLL. Okay, so a lot of packages will call this as NLL loss, like which is basically negation of log likelihood. Yeah.
Why is it better to minimize instead of max?
Oh, it is not better to minimize over instead of maximize. Okay, so they are both equal, like they're always same. It is just that like it's like a convention, right? Like, so we always do gradient descent, we don't do gradient ascent. But on the other hand, like for example, like if you want to do maximizing log likelihood, you will do gradient ascent. Like you go up the slope. But since we always like gradient descent, like so we are just converting into NLL. So they're not, one is not better than the other. They are both same. Okay. It is just that I don't want you to be confused when you read one textbook which says, oh, we are minimizing the NLL. Like so what is NLL? It is nothing but minus of log likelihood. Is that clear? Okay. But for today's lecture, like we are just going to focus on the log likelihood, not on NLL. Okay, so probably we can do NLL when maybe in one of the future lectures, like so when we do gradient descent for these kind of algorithms. Okay, so for now we are going to do closed form solutions. So let us just do maximum likelihood. Okay, so we're going to come up with the maximum likelihood solution for GDA. Okay, so now maybe I will rewrite our ln p function because we are going to use this to compute. We are going to differentiate this. So ln p is given by summation over n is equal to 1 to capital N, p of n ln pi, the first Gaussian, right, plus 1 minus t of n ln 1 minus pi. I wish I can write neater with the same speed. Xn given mu2 sigma. Okay. Okay. Now we need to compute pi, we need to compute mu1, we need to compute mu2, and we need to compute sigma, right? So we're going to do all those things manually. Okay. So first we are going to maximize with respect to pi. Okay. Or in other words, dou ln p by dou pi, you set it to 0, and then you find the optimal pi. Okay, so how do we do that? It looks like a very complex equation, okay, but the easy thing here is all these parameters are in only one part of these equations. So we can just consider the rest of the part as constant. When you differentiate, the constant goes away, right? So now you can see that, okay, we are interested in pi. So where does pi show up? So there is ln pi here, right? There is ln pi multiplied by Gaussian. So that can be separated as ln A, ln B, right? So there is only ln pi here, this term, and this term, right? So the rest of the things, when you differentiate, it becomes 0. So basically, summation over n is equal to 1 to capital N, T of n ln pi, plus 1 minus T of n ln 1 minus pi, okay, plus some constant. So I'm just restructuring the equation. I don't care about the constant because when I differentiate, it goes to 0. Okay. Now I can differentiate this with respect to 0, like pi. So differentiate with respect to pi and set it to 0. Okay. So it's very easy. So summation over n is equal to 1 to capital N, T of n. When I differentiate ln pi, can someone tell me what is differentiation of ln pi? Yeah. 1 over pi, okay, plus 1 minus T of n. Now we need to differentiate ln 1 minus pi. What is it? It's 1 over 1 minus pi, then you again differentiate 1 minus pi, so it becomes minus, you get a minus 1, right? So the whole thing equal to 0. Okay, so now summation over n is equal to 1 to capital N. I'm going to put all the things together, okay? So T of n multiplied by 1 minus pi minus 1 minus T of n multiplied by pi. The whole divided by pi into 1 minus pi is equal to 0. Okay, so now we are setting it to 0, so the denominator can be moved to the right hand side, so that disappears. So you just have summation over n is equal to 1 to capital N, T of n minus T of n pi, okay, minus pi plus T of n pi is equal to 0, right? So this cancels. So you get summation over n is equal to 1 to capital N, T of n minus pi is equal to 0. Okay, so maybe let me bring this to the next page. Okay. Now the second term, right? So it is not dependent of n. So you are only having n times pi, right? So this becomes summation over n is equal to 1 to capital N T of n minus n times pi is equal to 0. So pi is given by summation over n is equal to 1 to capital N T of n divided by capital N. Okay. If n1 is equal to number of data points in class 1 and n2 is equal to number of data points in class 2, okay, so then we know that the upper part of this fraction is basically 1 whenever there is a data from class 1 and 0 otherwise, right? So this is equivalent to n1 divided by n1 plus n2. So that is our answer for pi. Okay. Now, if you think about it, this is a very intuitive prior probability, right? Like, so what does this prior probability tells us? It tells us that if you have a data set which has 100 examples, let's say, out of which 60 are class 1 and 40 are class 2, okay, then the prior probability pi is given by 60 by 100, which is 0.6. Okay, so in some sense, it's a very intuitive answer, right? Like, so that is what maximum likelihood solution is giving us. Okay, so when I ask you to compute yourself, like by saying, okay, there are 60 class 1 and 40 class 2, what is the probability of class 1? You will intuitively say it's 0.6, right? Like, so now maximum likelihood gives you theory that it is indeed a reasonable answer. Okay, now you could have guessed what would be the value of mu1. Anyone? If I do this maximum likelihood solution, what do you guess is the value of mu1? Okay, there are some answers in the chat, but I want to hear other answers as well. So what would be the maximum likelihood solution for mu1? So we are going to do the process, but you can easily guess now, given I tell you this is what pi is. So we are going to do maximization with respect to mu1. But any guess on what it would be? Sorry? The mean of what? Yeah, so an intuitive answer here is like mu is going to be the mean of all the data in the first class. Okay, well, that is what we are going to see now. Okay, so like maybe it's worth copying this equation again, because now we are going to consider only parts of this equation which corresponds to mu1. Okay, I'll put this equation here. Now first we can observe that mu1 is there only in this region. Right? So you don't have any mu1 in the second one. So the second one is a constant. So the other, even in this string, like the pi is a constant. So I can rewrite this as summation over n is equal to 1 to capital N. Okay. T of n ln just the Gaussian mu1 sigma. Okay. So the whole thing plus some constant. We don't care about the constant. Okay. Is that clear? So now if I write it this way, so then this becomes, so ln of the Gaussian. So now we know that the Gaussian has a bunch of terms there, right? Like including the x function, right? Like so this becomes minus 1 over 2 summation over n is equal to 1 to capital N T of n x of n minus mu1 transpose sigma inverse x of n minus mu1 plus constant. Okay, so anything else in the Gaussian's equation, like 1 over d power 1 by 2 or 1 over sigma power 1 by 2, they are all constants, so they go away. Okay, so because in this case we are only caring about mu1. Okay, so this is what the mu1's terms are. So now we can differentiate this and set it to 0. So when you differentiate this with respect to mu1, okay, so maybe I'll copy this to the next page. Okay, so I want to differentiate this with respect to mu1, differentiate with respect to mu1 and set it to 0. Okay, so how do I do that? So summation over n is equal to 1 to capital N. T of n is a constant. So you have x square here, right? So sigma will also go away because sigma is divided by sigma. So it goes to the other side when you differentiate with respect to 0. So all you have is x square. So when you differentiate x square, you get 2x, right? So 2 and 2 cancels. So you would just get x of n minus mu1 is equal to 0. Okay. Now you can see that. Okay, maybe I'll rewrite it. Okay, so summation over n is equal to 1 to capital N. T of n xn, okay, is equal to summation over n is equal to 1 to capital N T of n mu1. Okay, now we know this value. So what is this? If we sum all the TNs in your data set, what would that number be? It is just the number of examples from class 1, right? It is n1. So this becomes n1 times mu1 is equal to summation over n is equal to 1 to capital N T of n xn. So mu1 is equal to 1 over n1 summation n is equal to capital 1 to capital N, T of N, Xn. Is that clear? So this is what we predicted, right? Like, so we predicted a mean over all the examples from class 1. So this sum is going to be giving 1 weightage for examples from class 1, 0 weightage for examples from class 2. So it's the sum of all the examples from class 1 divided by total number of examples in class 1. Okay, so this is mu1. Now I'm not going to derive mu2, but similarly mu2 is given by 1 over n2 summation over n is equal to 1 to capital N, 1 minus T of N. Excellent. Is that clear? Okay. So finally, what is left? Like, so what is left is just sigma. So maximization with respect to sigma. Okay. Okay. So these were simple differentiations I showed you easily. The maximization with respect to sigma is a bit more involved. Okay, so we are not going to do that. I'm going to directly give you the answer. You can trust me, and you can go back and try to do it by yourself. So sigma is given by n1 by n s1 plus n2 by n by s2. Okay, where s1 is just the covariance for data from class 1. So it's a very intuitive answer, so you can easily trust that this is correct. But I encourage you to go and try proving it by yourself. Okay, so xn minus mu1 transpose. Similarly, s2 is given by 1 over n2 summation n belonging to C2, xn minus mu2, xn minus mu2 transpose. Is that clear? Okay, so now I have found all the parameters of the Gaussian discriminant analysis. So we have found what is pi. It's basically the average probability, like average of the frequency of the class 1. And we found mu1, which is basically the sample average of all the examples in class 1. We found mu2, which is the sample average of all the examples in class 2. And then we found sigma, which is basically average of the covariance from both the classes. Okay. Now, I have given you all the equations. So can you implement GDA, like, and compute the class probabilities? I think we have seen all the essence of the algorithm, right? So you should be able to implement this and compute the class probabilities. And that is going to be your second assignment. Okay. Okay. Now going back to our assumptions, right? We had two assumptions. So the first assumption was the class conditional densities are Gaussian. Okay. We are not going to relax that assumption today. We will relax that assumption next week. Okay. But there was the second assumption, which is easy to relax. Can someone tell me what was the second assumption?
The same covariance.
Yeah, so the classes have same covariance matrices, right? So now what happens if I remove that assumption and have sigma 1, sigma 2 to sigma k for k classes? So then you have these x squared terms, right? Like, so now you can do similar things that we did now for QDA, like for this x squared term, like the quadratic term based GDA, okay? And that has a name. It's called quadratic discriminant analysis, or QDA. Okay, but we are not going to derive the QDA here, like so, but you know what is a QDA. Okay, so now let us look at some examples. Okay, so here you see first a two-class problem where I'm using GDA. Okay, so I think even the notes calls it LDA, so make it GDA. Maybe this is a right time to make a quick note. So this algorithm, Gaussian discriminant analysis, is called by two different names in different textbooks. Okay, so some textbooks are going to call this as GDA. Some textbooks are going to call this as LDA, linear discriminant analysis, because it's a linear model, like generalized linear model. Okay, we will stick to the term GDA instead of LDA because we are going to see, well, LDA is one of the most overused abbreviations in machine learning. There are at least 3 algorithms called LDA. So we're going to see another algorithm, which is also called LDA in the second half of the course. So to avoid the confusions, we are going to call this algorithm as GDA. But your textbooks might call it as LDA. So they are both the same, okay? So sometimes called LDA or linear discriminant analysis. Okay. Now, here you see that there are two classes. So the circles that you are seeing is the Gaussian distribution. So this is the first Gaussian distribution that you are fitting. This is the second Gaussian distribution that you are fitting. And the class boundary is linear, right? Similarly, this is an example for 3-class setting. And you can see that you have this nice boundary between the 3 classes, but it is all linear. Okay. Now, as you can notice, the Gaussians look very similar, right? It's not a coincidence, like it's because the covariance matrices are shared. So only the mean of the Gaussians are shifting, but the shape of the Gaussian is exactly same, okay? However, if you move to QDA, which doesn't have this shared covariance matrix assumption, now you can see a lot of interesting things happening. Like, so first of all, you have nonlinear decision boundary. You have a quadratic like function, right? So it's a nonlinear decision boundary. So you can have models like this, which you cannot have with LDA or GDA, right? So, and second of all, you can see that the Gaussians, like you can see that this is a smaller circle. This is more elongated circle, right? So now you have this relaxed state where like you can have different shapes of Gaussians for each classes, okay? Now, so here is another interesting example where, can someone tell me like what are the assumptions that I have? I made some assumptions to come up with this boundaries. Can someone tell me what are the assumptions in this final example? Yeah?
Either the top 2 classes share a covariance matrix, but now with the third one?
Yes, well, that's what we have done here, okay? So we made an assumption that the top 2 classes share the covariance matrix, and the third one has its own covariance matrix, okay? You can mix things like that. So now you'll have just one sigma to represent the top 2 classes, and you have the second sigma for the third class. So if you share, obviously the decision boundary is linear, as you can see here. When you don't share, the decision boundary is non-linear. Is that clear? Any questions about GDA? Yeah? Yeah.
How did we come about to making some of these choices? All of these 2 share the same covariance matrix, these 2 don't.
That's a very good question. So the question is, how do you make this choice of which classes to share, which to not share? Okay. Well, okay, this is where the domain knowledge comes into picture, right? So like as a machine learning researcher or an engineer, like so when you're working on a problem, the problem could be from any domain. It could be a medical application or it could be a financial application, right? Like so you will have domain experts who will tell you this is what our problem is, right? Like so now this is one place where you can get their feedback, and they might tell you, like for example, if it is a medical application, the doctor might tell you, right? Like so they might tell you like which classes are related, which classes should have similar behaviors and so on. So if you have such domain experts knowledge, this is one easy place to integrate, right? Like you'll just say, oh, okay, these 2 classes should be similar, so I'm going to share their covariance. Or the most general aspect is just not share anything, okay? But we are going to talk about that after break, like the trade-off between sharing and not sharing. But to give you more information or more to this answer, in the future, okay, so we just get started with generalized linear models, right? Like so as we get to more and more complex models, right? Like so most of these things will be automated. So like we will reduce these prior knowledge and be completely dependent on the data to learn these things in the future. But for now, like one step at a time, like so like you're just moving from linear models to generalized linear models. And like I think today we also learned a new objective function. Instead of just always minimizing the least square, now if you have a probabilistic model, you know how to maximize the likelihood or log likelihood, or how to minimize the negative log likelihood. They're both same, okay? So probably we will stop here for a 10-minute break, and then we will talk about this trade-off of sharing versus not sharing.